In this session, we're going to be going over complex, or otherwise known as imaginary numbers. So up until this time, we have not been able to take the square root of a negative number. But now we're going to say that we're going to let I, the variable I, equal the square root of -1. Now if we were to square I, so if we wanted to find I squared, we would get just a -1. If we wanted to cube I, we would get a -I. And if we wanted to take the fourth power, the I to the fourth power, take I to the fourth power, we get just a +1. Now, knowing this, we will be able to find the square root of negative numbers. These four are the only i's that you need to know. Now, if you want to find I to the 5th, it's just going to be I. I to the 6th, I to the 7th, I to the 8th, I to the 9th, I to the 10th, 11, 12, 13, 14, 15, and so on. It goes in cycles. Now if we wanted to find, let's say, I to the 683rd, what we do is we take this power and divide it by 4, because we have 4 different options to choose from. If we do this, we'll get 1 here with a 2, 7, 0 with a remainder of 3. Now whatever the remainder is, we align that with the exponent on our I, and it would be equivalent to that. So I to the 683rd would have a remainder of 3, so that would correspond to I to the 3rd. So this I to the 683 would just be -I. Now I to the 4th is the same as I to the 0, because if we have a remainder of 4 when we're dividing by 4, then we actually didn't have a remainder of 4 at all. Another 4 could fit into that number, so the remainder would be 0. And I, of course, would just be a remainder of 1, because it's I to the 1st. Now how do we use I? Well, let's say we want to find the square root of -9. If we're looking for a real solution, there isn't one. But if we're looking for an imaginary one, it's very simple to find. Structurally, this is saying the square root of -1 times the square root of 9. The square root of -1 is I, the square root of 9 is 3. So this square root of -9 would be 3 times I. Now, a shortcut is to think if we have the square root of -144, or a square root of negative anything, we can just simplify the square root like we normally would, but take that negative and just throw an I out there. Now we always leave our solutions when we're dealing with i's in the form a plus bi, where a is the real part and b is the imaginary part. Now we have something called the conjugate, which we'll use in a little bit. If we have a plus bi, the conjugate would be a minus bi. If we had a minus bi, the conjugate would be a plus bi. So the real part stays the same, but the imaginary part changes its sign. Let's take a look at an example problem. Let's say we have 1 plus the square root of -49. Well, we know the square root of 49 is 7. With that negative, it just means we have to throw an I in there. So this would be equal to 1 plus 7i. Again, this is in our a plus bi form. So now let's say we want to take a look at 8 plus 3i minus -7 minus 2i. We can normally treat I as just any other variable. So this would be 8 plus 3i. We have to distribute this negative to each term, plus 7 plus 2i. So this would become 15 plus 5i. Now let's say we have 4 minus I times 2 plus I. So to do this, we're going to need a FOIL. So we're going to get 8 plus 4i minus 2i minus I squared. If we combine like terms, we get 8 plus 2i minus I squared. But we know what I squared was. Remember, I squared is a -1. So we need to plug that in for I squared. So this then would become 8 plus 2i minus negative 1. This minus negative 1 would become plus 1. We get 9 plus 2i for a final answer. Now if we look at a different problem, this is where we will use a conjugate. Let's say we have 3 plus the square root of negative 16 divided by 4 minus the square root of negative 9. The first step is to simplify the numerator and the denominator independently. This would then change our problem to 3 plus 4i divided by 4 minus 3i. Now when we leave our answer, when we have our final answer, we don't want to have any i's in the denominator. Very similar to how we don't want a radical left in the denominator. Now if we multiply then the top and the bottom by the conjugate of the denominator. Since it's 4 minus 3i, the conjugate would be 4 plus 3i. And since we're multiplying the top and the bottom of this by the same thing, it's like multiplying it by 1, which does not change the equality of our problem. So now we'll need to FOIL both the top and the bottom. On the top, we'll get 12 plus 9i plus 16i plus 12i squared. On the bottom, we'll get 16 plus 12i minus 12i minus 9i squared. So notice on the bottom how we have plus 12i minus 12i. They cancel out, and that's exactly why we multiplied by the conjugate. We wanted to get that I term gone. So now on the top, substituting a negative 1 for I squared, we'll have 12 plus 25i minus 12 divided by, and then the bottom, by substituting a negative 1 for I squared, we'll get 16 plus 9. Now on the top, we have just a 25i. On the bottom, we have a 25. The 25's cancel each other out, and we're left with an I as our final solution.